Section 6.2, the binomial probability distribution. We will look at these four objectives in this section. First, let's look at the criteria for a binomial probability experiment. An experiment is said to be a binomial experiment if, first, the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. 2, the trials are independent. This means the outcome of one trial will not affect the outcome of the other trials. 3, for each trial, there are 2 mutually exclusive or disjoint outcomes, either success or failure. And 4, the probability of success is fixed for each trial of the experiment. So here's some notation that we use in the binomial probability distribution. The number of independent trials is denoted by n. P will be the probability of success, so that means that 1 minus p is the probability of failure. We'll let x be a binomial random variable that denotes the number of successes in n independent trials of the experiment. So our value of x must be a value between 0 and n inclusive. So let's look at some examples. We want to identify binomial experiments. In A, a player rolls a pair of fair die 10 times. The number x of 7s rolled is recorded. So we want to identify whether or not this is a binomial experiment. First thing to look at is, are there a fixed number of trials? And yes, there are n equal 10 trials. Number 2, the 10 trials are independent, meaning that when I roll the dice the first time, it will not affect the outcome for the second roll, and so on. Thirdly, are there only 2 possible outcomes? In this case, yes, either we get a sum of 7 or we don't. And fourthly, is the probability of success constant? Yes, in this case it is, because we are dealing with a fair set of dice. So this is a binomial experiment. For B, the 11 largest airlines had an on-time percentage of 84.7% in November 2001, according to the Air Travel Consumer Report. In order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 that were not on time. The number of flights X that need to be selected is then recorded. So we want to know if this is a binomial experiment. And we can already tell that it's not. There was not a fixed number of trials. The official simply selected flights until she found 10 that were not on time. So that was not a fixed number. In C, we have a class of 30 students where 55% are female. The instructor randomly selects 4 students, and the number X of females selected is recorded. So is this a binomial experiment? This one would not be either, since the trials are not independent. If one of the students selected is female, then that affects the probability that the others will be female, since it affects how many females are left in the room. Objective 2. We want to compute probabilities of binomial experiments. For the binomial probability distribution function, the probability of obtaining X successes in n independent trials of a binomial experiment is given by this formula here, where P is the probability of success. And note that NCX would be the formula we had for a combination of n objects taken X at a time. So first let's look at some phrases that we'll see as we work some of these problems and what the math symbol would be that goes with it. The phrase at least, or no less than, or greater than or equal to. those all mean the same thing. And we see the math symbol of our inequality greater than or equal to. These two phrases, more than or greater than, mean the same thing, and our symbol is the greater than inequality symbol. The phrase fewer than or less than, we see the symbol for our less than inequality symbol. No more than or at most or less than or equal to. These all mean the same thing, and we see the less than or equal to inequality symbol. Exactly or equals or is, all of those phrases mean equals, and we use the equal sign for that. So we want to use the binomial probability distribution function in these examples. So according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what is the probability that exactly 5 have 3 or more cars? So recall our probability for x. We have NCx times p to the x times 1 minus p to the n minus x. So when we were computing the probability that exactly 5 have 3 or more cars, out of 20, we have 20 C5, then our probability was 35%, or 0.35, which will raise to the x, or fifth power, 1 minus our 0.35, now raised to the 20 minus 5. And when we work this out, we get a value of 0.1272. So we could put this in our calculator. We type in 20, and then we go to Math, arrow over to PRB, choose number 3 for NCR, and then 5. Then we'll have our parenthesis, 0.35. We raise that to the fifth power, and then we multiply that by 1 minus 0.35. Raised, and we'll do parentheses here for 20 minus 5, which you could also have gone ahead and calculated as 15. So we see our value of 0.1272 here. For part B, in a random sample of our 20 car-owning households, what's the probability that less than 4 have 3 or more cars? So the probability that our value is less than 4, that's saying the same thing as the probability that x is less than or equal to 3. So it's every value from 3 down, which includes 0. So we want to take the probability of it being 0, plus the probability of it being 1, plus the probability of it being 2, plus the probability of it being 3. So if we calculate these individually, we'll get approximately 0.0001, then plus 0.0020, plus 0.0100, and then plus 0.0323. When we sum those, we'll get approximately 0.0444. In a random sample of 20 car-owning households, what's the probability that at least 4 have 3 or more cars? So remember that our word at least means greater than or equal to. So we're looking at the probability that x is greater than or equal to 4, which is also the same as 1 minus the probability that x is less than or equal to 3. So we could take all of the probabilities for every value from 4 all the way up to 20 and add them together. But knowing that they all add up to 1, and we've already found the values for 0 through 3. So knowing that, we can simply take 1 minus that value to get the sum of the others. So we would have 1 minus our 0.0444 that we found in the previous slide, and we'll have 0.9556 approximately. So we just looked at using our formula to find those, and it can take quite a while to do it. Let's look at another method. We can use table 3. In our table, we see our n value listed on the far left, with the next column being the values for x, which was our number of successes. And then across the top is our probability values, or p. So we want to look again at part A, where we found the probability of exactly 5. So looking at n is 20 and going down to where x is 5 and over to our column P is 0.35, we see the value we found by doing it with our formula, which is 0.1272. In the same way, the probability of less than 4, remember that is the probability that x is less than or equal to 3. So it was the sum of our probabilities for 0 through 3. So we can look at the table and we see n is 20 and x at the very top is 0, 1, 2, and 3. We go over to the column where p is 0.35 and we can simply just add those values together. And this is a little more precise. So we see that we actually get 0.0445 here. And now the at least 4, so greater than or equal to 4, we could take all of the values in our column for 0.35 from 4 all the way up to 20, and notice that the last several are all just zeros. But you could add all of those together, or simply do what we did in the previous example and do 1 minus the probability that x is less than or equal to 3. And remember that we got 0.9556 before, but this time we would get 9555 with our more precise value. And there is one last method we can use to do this. We can use the calculator. And the first step, we press second, and then the vars key, which is right next to the clear button. This will help us access the probability distribution menu. Then we highlight Binomial PDF. So I'm going to continue to arrow down until I see that on the screen. And so I want Binomial PDF and not CDF. So I'll hit enter on that. With Binomial PDF on the home screen, we type the number of trials n. So in our example here, we're going to let n be 15. Then a comma. Then the probability of success, p, which for our example is 0.3. And then a comma. And then our number of successes, x, which in this case we'll put 8. And close our parenthesis and then hit enter. And we see our value here for the binomial distribution. So let's do it again. For the value for part A from our previous example, where we had 20 was n, 0.35 was our probability, and 5 was our number of successes. Remember, we got 0.1272, and that's what we get when we put it in the calculator. So we've looked at 3 different methods. You can use the formula, you can use Table 3, or you can use Binomial PDF on your calculator. Objective 3, we want to compute the mean and standard deviation of a binomial random variable. A binomial experiment with n independent trials and probability of success p has a mean and standard deviation given by these formulas. Mu sub x is equal to n times p, and sigma sub x is equal to the square root of n times p times 1 minus p. So let's look at an example. According to the Experian Automotive, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, we want to determine the mean and standard deviation number of car-owning households that will have 3 or more cars. So the mean is equal to n times p. N is our sample size, which was 400. And p is the probability, or 35%, so we write that as 0.35. And when we multiply that together, we get a value of 140. Our standard deviation is equal to the square root of n times p times 1 minus p. So we have the square root of our 400, which was our sample size, p, which was 0.35, times then 1 minus 0.35. And we'll get a value of approximately 9.54. Objective 4. We want to construct binomial probability histograms. Let's look at an example. For each histogram, we want to comment on the shape of the distribution. For part A, we want to construct a binomial probability histogram with n equal 8 and p equal 0.15. So here we've listed a table with our x values 0 through 8 and then the probability of x, which we can find either in the table or using a calculator or the formula. And here then is our binomial histogram. The x values are on the horizontal and the probability values are on the vertical. Notice that this distribution is skewed right. For our next one, we want to construct a binomial probability histogram with n equal 8 and p equal 0.5. So we have listed our values for x, 0 through 8, and then the probabilities. And notice how we have our peak in the middle at 4, and they repeat kind of going down from there. So we see that our histogram looks similar to what we would have expected with that pattern. It's symmetric and approximately bell-shaped. And lastly, we want to construct a binomial probability histogram with n equal 8 and p equal 0.85. So again, we've listed our x values and then the probability of those. And you see that it's very similar to part A, just in reverse. So it should make sense then that this probability histogram would be then skewed left. So in our previous example, we were looking at what role the probability played in the shape of our distribution. But now let's have a look at the role n plays. So we're going to leave our probability the same this time, and we're going to change the value of n and comment on the shape. So in this one, we want to construct a binomial probability histogram with n equal 25 and p equal 0.8. And here we see that picture. Notice that this one is skewed right. And now let's look at what happens when we increase n to 50, but leave the probability at 0.8. And we see that this one is only slightly skewed right. And now we'll increase n to 70 and leave our probability at 0.8. And we see now that this one is even closer now to being in a bell shape. So this appears to be bell-shaped. So what we see then is that for a fixed probability of success p, as the number of trials n in a binomial experiment increase, the probability distribution of the random variable x becomes bell-shaped. As a general rule of thumb, if n times p times 1 minus p is greater than or equal to 10, then the probability distribution will be approximately bell-shaped. So let's use the empirical rule to identify unusual observations in a binomial experiment. The empirical rule states that in a bell-shaped distribution, about 95% of all observations lie within 2 standard deviations of the mean. So that means that they lie between the mean minus 2 standard deviations and the mean plus 2 standard deviations. Any observation that lies outside this interval may be considered unusual because the observation occurs then less than 5% of the time. So let's look at an example, and we want to check for unusual results in a binomial experiment. So remember that according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. A researcher believes this percentage is higher than the percentage reported by Experian Automotive. He conducts a simple random sample of 400 car-owning households and found that 162 had 3 or more cars. Is this result unusual? The first thing we need to do is to find the mean. Remember that that value is n times p. So n was 400 and p was 35% or 0.35. So recall that we found this value before to be 140. And our standard deviation is n times p times 1 minus p, the square root of that. So we have the square root of 400 times 0.35 times 1 minus 0.35, which we found before to be approximately 9.54. So we list those again here. And what we want to calculate is the mean minus 2 standard deviations, and then the mean plus 2 standard deviations. So we have our value of 140 minus 2 times our 9.54. And over here we have the 140 plus 2 times that 9.54. So we get an interval then of 120.9 up to 159.1. So what we're saying then is that 95% of our values should lie between those two numbers. So our value of 162 is greater than our highest value, which means it's unusual, since it would be occurring less than 5% of the time.